Harsh. Okay, let us start. Okay. First of all, sorry for the inconvenience. Today morning, director sir joined a lecture from my Google Meet ID so that I could not deliver lecture scheduled for digital data communication. I'm sorry for that. So in our previous lecture, we studied about the comparison of FM and PM as well as FM and AM. With the help of two tables, we compared these three techniques with one another. Now let us move to the remaining two topics of our syllabus, that is Narrowband FM and Wideband FM and their modulation index. So since this is a modulation technique, so all modulation techniques are somewhat similar to one another, and how they are similar, it is in the sense that the process is same. And what is the process? In process, we know we have a message signal, we have a carrier, a message signal is superimposed upon a carrier, we get an instantaneous frequency. Instantaneous frequency further should have two components. One component should include the carrier part, the another component should include the modulating part, that is modulating signal. In our previous lecture, many a times we have talked about a term that is frequency deviation. This is the term which is generally used in case of narrowband FM and wideband FM, and it is this term which will decide about the number of bands present in the spectrum. This term is a product of the Kf, that is constant factor in frequency modulation, Kp, a constant factor in phase modulation, and Em, which is nothing but the modulating voltage, which is amplitude of the modulating voltage, and it remains constant. So what will be the maximum frequency in case of frequency modulation or phase modulation? This maximum frequency will depend upon the carrier frequency plus minus the frequency deviation. So this frequency deviation depends upon two factors, that is constant factor Kp or Kf and amplitude Em. So the maximum frequency should also depend upon the type of modulation technique, that is FM or PM, and the maximum amplitude of the modulating signal or the voltage. Further, the constant Kp or Kf we have studied in the modulation index. So obviously now the maximum frequency present and the number of maximum bands, side bands present in the modulation technique will depend upon the modulation index. If we change modulation index from 0 to half, half to 1, 1 to 2, 2 to 50, 50 to 200 or so, correspondingly, the more and more number of side bands will occur and they will have appreciable magnitude. Now let us talk about the mathematical expression for the FM. In mathematical expression, let us assume that we have a amplitude EC, which is the amplitude of the modulating signal, is represented by a phasor. In your lower class, somewhere you must have studied about the Phasor diagrams. These Phasor diagrams are nothing but the angular variation of any physical quantity over time. So here angular variation is of what? Angular variation is the EC, modulating voltage amplitude, and it is given by a rotating vector. Let us say this rotating vector gives us the modulating voltage, modulating signal in terms of the frequency modulation technique. This is given by expression St is equal to EC sine capital F omega C omega M. Equation 4.17 has two frequencies, omega C and omega M. Why it has two frequency? Because it is a modulated signal which is obtained after the superposition of the modulating signal on the carrier wave. So it should have both the components, the carrier frequency and the modulating frequency. Now let us say we can write the frequency of the modulating signal as omega, and it is equal to omega c plus KEM cos omega mt. So once again it has two parts, and these two parts are the carrier frequency part and the modulating signal part. Now we know that modulated signal is represented in terms of the spatial variation in theta. In amplitude modulation technique, you know the change in the amplitude according to the message signal is recorded in the modulated signal. Here in FM and PM, the change in frequency and change in phase are recorded in terms of the angular variation. So the modulated voltage will have theta t is equal to omega dt, that is angular frequency will change in time and which will change its angular part, that is angle theta t. So omega dt should also have two terms. It should have a carrier term. It should also have a message signal, that is modulating. So after substituting this in equation 4.21, we can take omega c common from equation 4.21, and after taking omega c common, we will get 1 plus KEM by omega c cos omega mt. Now we have to integrate this cos omega mt, and you know integration of cos omega t will be sin omega t divided by omega. So cos omega mt will be integrated. Its integration will be equal to sin omega mt divided by omega m. And now if we multiply omega c inside, we will get omega ct plus KEM omega c sin omega mt divided by omega m into omega c. So this term omega c will get cancelled over here, and after cancelling omega c in the numerator and denominator, we will get theta t is equal to omega ct plus KEM sin omega mt divided by Fm. So we have already discussed that what is KEM. KEM is our deviation term, frequency deviation term. So in place of KEM, we can substitute this delta F, and after substituting the delta F, the modulated voltage or modulating signal will become EC into sin omega ct delta F by delta M. Now this delta F by delta M is called as our modulation index. This modulation index is generally 0 to 1 or less than 1 in case of amplitude modulation, whereas in case of frequency modulation and phase modulation, it can be equal to 1, it can be higher than 1 as well. So modulation index can be defined as the frequency deviation divided by modulating frequency. Fm is the modulating frequency, delta F is the frequency deviation, which is equal to Kf into Em or Kp into Em, depending upon phase modulation or the frequency modulation. So here one point is important, that the number of sidebands present in the modulating signal are proportional to the modulation index. If we change the modulation index, then accordingly the number of sidebands present will change. If we change modulation index from MF is equal to 1 to MF is equal to 2, the number of sidebands present will increase from 2 to 4. Deviation ratio is another term which is equal to the division of maximum deviation divided by maximum modulating frequency. What is this maximum modulating frequency? This is the frequency present in the message signal which we have to modulate. Now the last topic of our syllabus, Unit 1, Part 2, that is Narrowband FM and the Wideband FM. So this Narrowband FM, as the name suggests, it will have narrow bands, that is only the carrier frequency will be present, as well as the upper sideband, lower sideband will be present. So expression 4.31 represents the narrowband FM, which has a carrier wave. The first term is a carrier wave. The second term is a upper sideband term. The third term is a lower sideband term. So this narrowband FM has three terms. First carrier, second upper sideband, then lower sideband. And where these bands locate in the spectrum, these will fluctuate around carrier frequency, that is omega c, and these are represented with the help of plus and minus sign around the barrier, that is carrier. So around carrier, the upper sideband and lower sideband will be present. And what are their locations? Their locations are decided by omega c plus minus omega m on the spectrum line. This negative sign in expression is because of the phase shift of 180 degree in the lower sideband, and the maximum modulation index is equal to 1, and the frequency deviation, that is how frequency can deviate from upper sideband and lower sideband, are 5 kilohertz. So how to generate this narrowband FM? This narrowband FM can be generated with the help of a block diagram. In the block diagram, we require a message signal which will pass through an integrator, and there will be a carrier oscillator which will provide the carrier frequency. And when carrier frequency and the integrator outputs are fed into the balanced modulator, we will get a modulated signal which is equal to EC KP XT sin omega CT, and this minus degree, and ST will be the final output of the this block diagram, which is for the frequency modulation technique. Now let us study the mathematical part as well. In mathematical part, we have a message signal, we have a modulated signal. This modulated signal has two parts: carrier part and the modulating voltage part. Carrier part is represented by carrier frequency, that is omega CT or 2 pi FCT, and the modulating signal is written in terms of the integration of the XT/dt. Why integration? Because the signals can be repetitive signals like sinusoidal, cosine wave, the triangular wave, the rectangular wave, etc., which has certain time period after which they repeat themselves. So integration will involve the time period of the type of the signal. So after knowing this carrier and modulating voltage in modulated signal, we can rewrite this equation in terms of angular frequency, because we know the relationship between the angular frequency and linear frequency is that omega c is equal to 2 pi fc. So in place of 2 pi fc in the above equation, we substitute omega ct plus 2 pi kf xt dt integration. Now we have to use here a property of the exponential function and cosine function, that we can write trigonometric function in terms of exponential function, and we can also rewrite the exponential function in terms of the trigonometric function. So here we have written the cosine function in terms of the exponential function, and after writing the exponential function and substituting for integration of xt dt at gt term, the modulating signal is equal to EC exponential j, that is iota. You may write iota here as well. For j, they both have the same meaning. Cos omega ct plus kf gt. Now here this term kf gt is important. If this term is very much smaller than 1, then we have a narrow band FM case, that is our bands are narrow and we will have only limited bands present, that is 2 bands around the carrier frequency. Wideband FM. In wideband, instead of 5 kilohertz deviation, we can have a deviation up to 75 kilohertz. So due to wide deviation, we can have wideband FM, and they are used for FM radio and the TV broadcasting. Now the relative comparison of the wideband FM and the narrowband FM. Modulation index is greater than 1 in wideband FM. In narrowband FM, it can be less than or is slightly greater than 1. Whereas in wideband FM, it is always greater than 1. It may go up to say 2, 3 or so. Maximum deviation is 75 kilohertz in wideband FM. In narrowband FM, the maximum deviation is 5 kilohertz. Range of modulating frequency is from 30 to 15 kilohertz. In case of narrowband, it is 30 hertz to 3 kilohertz. So you can see the variation in frequency range. In wideband FM, we can go up to tens of thousands of frequency. And in case of narrowband, we can have only up to 3000 hertz of the frequency. Modulation index is 5 to 2500 in wideband, where it is just slightly greater than 1 in case of narrowband FM or slightly less than that. Bandwidth in case of wideband, as the name suggests, wideband, it has 15 times higher than the narrowband FM. In narrowband FM, the bandwidth is small, as the name suggests, narrowband, approximately same as that of amplitude modulation. So narrowband FM has the similarity with the amplitude modulation in the sense that its modulation index is just less than 1 or just greater than 1, which is the case for amplitude modulation. Also, the frequency bandwidth is similar for FM and AM, narrowband FM and AM, whereas the bandwidth is 15 times higher in the wideband. Applications, entertainment, broadcasting can be used for high quality music transmission. Narrowband FM mobile communication like police wireless, ambulance, etc. Pre-emphasis and T-emphasis, that is the circuitry required to modulate and circuitry required to demodulate, are required in the both cases, wideband as well as the narrowband. Now let us understand some theoretical part of the wideband FM, as we have already discussed the narrowband FM. So wideband, the equation is similar to narrowband FM. That is, it should have a carrier, it should have band. In case of narrowband, there were only 2 bands present, but here now you can see with the carrier C here, we have first band, the second band, the third band, the fourth band. So this much number of bands are present in case of the wideband FM. And how these widebands are represented? They are represented with the help of Bessel functions. Do you know about the Bessel functions? Hello? Hello?
Yes, sir.
You must have studied in your lower class that these are the special class of functions which have some fixed values. Yes or no?
Sir, एक बार repeat करना आवाज.
These Bessel functions are the special class of functions which you have studied in your lower class, and these Bessel functions are dependent on some argument, and here the argument is modulation index. For a particular modulation index value, the Bessel functions have different values. I will show a table of variation of modulation index as well as the corresponding values of the Bessel functions of first order, second order, and so on. So this equation is important because this equation is similar to our amplitude modulated equation, frequency modulated equation, narrowband modulated equation, in the sense that all these equations will have 3 parts: carrier part, the upper sideband part, lower sideband. But here the number of upper sidebands and lower sidebands are 4 on the upper sideband and 4 on the lower sideband, which are represented by the frequency omega c plus omega m for first upper sideband, omega c minus omega m for the first lower sideband, omega c plus twice omega m for second upper sideband, omega c minus twice omega m for the second lower sideband, omega c plus 3 omega m third upper sideband, omega c plus 4 omega m fourth upper sideband. Similarly, omega c minus 3 omega m third lower sideband, omega c minus 4 omega m the fourth lower sideband. So we can summarize this wideband FM by saying that the FM wave consists of a carrier, which is clear from the equation. The first term is a carrier term. FM wave ideally consists of infinite number of sideband. How infinite number of sideband will be clear in the next slide, where we will show the different values of the Bessel functions of different orders for different values of the modulation index. The amplitude of the carrier and sidebands is dependent upon the Bessel function coefficients. Here you can see a table which represents on the x-axis, on the y-axis as the modulation index, and on the x-axis we have J, that is modulation index. Here this is J, Bessel function. So you can see for the 0, 1st, 2nd, 3rd and up to 15th order, if modulation index changes over here, then correspondingly there will be a change in the J values over here. And how graphically these values can be represented, the graph is shown in the slide which you can see. So the last slide for today's lecture, we can summarize the important points related to the spectrum of FM. The next slide will be only a picture related to the spectrum. As the values of J coefficients changes for different values of modulation index, we can have different sidebands. The negative sign in the J coefficients represents the 180-degree phase shift for a particular pair of the sideband. The carrier component does not remain constant, it depends upon the Bessel function, which depends upon the modulation index. For certain values of modulation index, the carrier component will disappear completely, and these values are called as the eigenvalues. Power in the transmitted wave is equal to Pt EC square by 2R. EC is the maximum amplitude of the carrier, R is the resistance. Now the spectrum of the FM wave will be like this. This part represents the upper sidebands, which are nothing but the addition in the frequency Fc plus FM, Fc plus 2FM, Fc plus 3FM, Fc plus 4FM. Similarly, in the lower side, Fc minus FM, Fc minus 2FM, Fc minus 3FM, and Fc minus 4FM, Fc minus 5FM or so. So this part represents the lower sideband, number of sideband. There is one thing you can surely note over here, that the amplitude is decreasing. You can clearly see the maximum amplitude is decreasing if the number of bands are more and more taken into account. Now the effect of modulation index, you can see in this figure, we have 3 bands present in the upper side band and lower side band when the modulation index was 1. When modulation index was changed to 2, the number of sidebands present was equal to 4. So on changing modulation index, the number of sidebands present changes from 3 to 4. And you know, if we go back to the previous comparative slide, in this slide, you have modulation index. I'm talking about point number 4, where I'm circling this tick. So you can see in wideband FM, the modulation index can go from 5 to 2500. So you can see if modulation index changes from m is equal to 1 to 2, we have number of sidebands present from 3 to 4. So you can assume what will be the number of sidebands present if we change the modulation index from 5 to 20.